In this video, I'm going to introduce you to organic reactions. Although the focus of this unit has been on naming various molecules, it's actually more relevant to learn how to synthesize various organic molecules. And so today's lesson is just going to be an introduction into this topic. So most organic reactions are examples of three broad types of reactions that can be identified by comparing the number of bonds to carbon in your reactants versus the products. So one class is a substitution reaction, in which case an atom or a group of molecules from an added reagent substitute for one in an organic reagent. So in other words, let's say you've got an alkane and you remove a hydrogen and substitute it with a halogen, for example. An addition reaction is where you take an unsaturated reactant and you saturate it. So that means you take an alkene and turn it into an alkane, or an alkyne is converted into an alkene. And an elimination reaction is the reverse of that. You take a saturated reactant and make it unsaturated. So you have an alkane and you remove some hydrogens and make a double bond, for example. So let's first start off with substitution reactions. And so in that case, what you're doing is you're taking a hydrogen atom or a group of atoms and you're replacing it with a different set. Okay? Now, carbon-carbon bonds and alkanes are difficult to break, which is why the hydrogen atoms are the ones that are typically substituted. And they're usually substituted by a halogen. Okay? Now, reactions with fluorine, so in other words, if you want to substitute a hydrogen with fluorine, it's very easy to do. But if you wanted to substitute a hydrogen with a different halogen, you're going to need different environmental conditions. You're going to need heat, you're going to need some ultraviolet light, for example. It's not as easy to do. Okay. So for example, here we've got ethane, and what we're going to do is we're going to remove the hydrogen on one of the carbon groups and add a single bromine. And so as a result, you end up with bromoethane as your product. That's a substitution reaction. And here, we're taking cyclohexane, adding bromine to it, and again, you get a substitution reaction. Here, over the arrow, which is also listed in the previous example, is an indication of its environmental conditions. So the triangle means that there's heat, and HV is just generic notation to indicate that light, probably UV light, is necessary to make this reaction happen. Now, in this reaction is a little bit misleading. It seems like this is an addition reaction. It seems like we're adding more bonds to the structure, but you've got to realize in this line structure there are two hydrogens attached to this particular carbon. It's implied that they're there. They're not drawn. And so we're actually taking one of these hydrogens away and we're adding a bromine to that carbon, to that particular carbon. Now, it's a completely arbitrary decision for me to select this particular carbon to substitute a bromine with. It really didn't matter. Now, an addition reaction is where you're taking an unsaturated hydrocarbon and you're making it saturated. Double bonds and triple bonds are a little bit more reactive when you compare them to alkanes. And so what we can do is when we can just add hydrogens back to those carbons involved with the double bonds, or you can add other things like a hydrogen halide or just a halogen, or in fact water can be added as well. So we'll take a look at some of those examples. Okay, so here, and each different type of addition reaction is given its own distinct name. So here we're going to add bromine to the double bond. So each carbon is going to be provided with its own bromine, and so because we're adding a halogen to both carbons involved in the double bond, this is considered a halogenation reaction. A similar concept, except for instead of a halogen, we're going to add hydrogen. In this case, we're going to run this reaction twice, so we're starting off with an alkene. Two hydrogens will be added to it to form an alkene, and then two hydrogens will be added to it again. So 2 moles of hydrogen will be added ultimately to form an alkane. And so to make this happen, you do need a catalyst of some sort, and your environmental conditions are listed here as well. Further examples of addition reactions could be a combination of the two. It's a hydrohalogenation reaction. So in this case, the hydrogen will be added to one of the carbons involved in the double bond, bromine will be added to the other, and in this case we get 2-bromopropane. You could add water to an alkene rather, and when you are adding water, it's sometimes simpler to look at water as being of the formula HOH, and by doing so, what that allows you to see that one of the hydrogens will be added to one of the carbons involved in the double bond, and the hydroxyl group will be added to the other double bond. So in this case, the hydrogen will be added to the first carbon, and then the hydroxyl group will be added to the second carbon. Now, we haven't learned to name alcohols yet, but you can see that this OH, this hydroxyl group, is given the functional group. It's called a hydroxyl functional group, and the suffix is OL. So you can see that it's attached to the second carbon, propan-2-ol. We won't focus on that too much, but this is another example of an addition reaction. It's called a hydration reaction when you add water. Now, in those two examples, for the first one, for the hydrohalogenation reaction, I told you that when we took propene and added HBr, we formed 2-bromopropane. So in other words, the hydrogen was added to the terminal carbon and the bromine was added to the carbon in the middle. But did it have to be that way? Could the bromine have been added to the terminal carbon, the carbon at the end, and the hydrogen have been added to the carbon in the middle? Same thing with the addition of water. When we did this example, the hydrogen from water was added to the terminal carbon, and the hydroxyl group was added to the carbon that was in the middle. Could it have been the other way around? Could the hydroxyl group have been added to the first carbon and the hydrogen been added to the middle carbon instead? And the answer is no, not really. There's a rule about that, and that rule is called Markovnikov rule. And another way of thinking about this is thinking about the rich getting richer. And when we talk about the rich getting richer, we're specifically talking about hydrogen. So if you are adding a hydrogen halide, or if you're adding water to an alkene or an alkyne, the hydrogen of those two will go to the carbon atom that has the greatest amount of hydrogen already. So the carbon that is rich in hydrogen will become even richer with hydrogen from an addition reaction. So for example, in this example here, we have to decide which of these two carbons is going to accept this particular hydrogen. So this carbon has 2 hydrogens. This carbon only has 1 hydrogen. So this carbon is, when you compare the two, this one is richer in hydrogen, and as a result, it will be the one that will accept the hydrogen from the hydrogen halide as a result. So let's take a look at another example here. What compound will be produced when water reacts with 2-methylpentene? And so again, we're going to look at water as being HOH. And so the question is, of these 2 carbons involved in the double bond, which one will accept the hydrogen from water? Okay? And so here's the same question just being redrawn. So when I look at the structure, I evaluate the 2 carbons that are directly involved in the double bond. Think of water as HOH, and the hydrogen of HOH will be added to the carbon that is richer in hydrogen. And then the other carbon, therefore, will get the rest of water. It'll get the hydroxyl group. So this carbon has no hydrogens at all. This carbon has 2 hydrogens. So it's that terminal carbon that's going to receive the hydrogen from HOH. And so as a result, this carbon gets the hydrogen. The second carbon here is the one that's going to receive the hydroxyl group as a result. Okay. Now, is that the only product that will be produced? Not exactly. If you were to actually do this in the lab, you would get both products present. In other words, all possibilities would occur. It's just that Markovnikov's rule helps you predict which product will be produced as a majority. Okay. So for example, with this example, 90% of our products would be 2-bromopropane, and the minority of the products would be the other possibility. Now, how do you know what those percentages would be? You wouldn't know. You'd have to actually carry that out and come up with some empirical evidence yourself. So knowing the percentages is not relevant. It's just knowing which product would be the major product. That's important. Okay. The elimination reaction is the reverse of the addition reaction. So what you are doing is you are forming a double bond, or sometimes you are forming a triple bond, and it really is the reverse of the examples that we did. So what it requires is that you are taking an alcohol, something that has a hydroxyl group, or you're taking alkyl halide, and you're removing those to form that double bond. The question is, where does that double bond form? And the rule that you're going to follow this case, it's the opposite rule of the addition reaction, but this rule is actually called Zaitsev's rule, and the rule is the poor gets poorer. So in the event where there's more than one possible location for your double bond, the alkene in greatest amount, the major alkene that's going to form, is going to correspond to the carbon that has the fewest number of hydrogens. Okay. So for example, let's say we have 2-bromobutane rather. Okay. So we're going to eliminate the halogen on that carbon. The question is, which other carbon will be involved in that double bond? So will it bond to the carbon to the left, or will it double bond with the carbon to the right? And so what you're going to need to do next is evaluate which of those two carbons is the poorest in hydrogen. So this has the carbon on the left has 2 hydrogens, the carbon on the right has 3 hydrogens. The one that has the fewest number of hydrogens will be the one that will form the double bond. So as a result, the double bond will form between the second and third carbons as a result. Okay. So let's take a look at another example here. So I've got 2-bromo-2-methylhexane. So the carbon that has the carbon that has the bromine attached to it, that will be removed. So this carbon will be involved in the double bond. So it's a question of which neighboring carbon will it double bond with. So at the one below it, the one above it, or the one in front of it. And so what you're going to do is you're going to see, these are all of our 3 possibilities. The question is, which one is the likely possibility? And so when I'm looking at these 3 carbons, this one has 3 hydrogens, this one has 3 hydrogens, this one has 2 hydrogens. So this is the bond that will, this is where the likely, is the likely position of where that double bond will take place. Now, so in other words, this is going to be the major product down below. Another way of looking at this example, so here's the exact same structure, just drawn as a line structure. This is the major product that's going to be formed. This product here is going to be the minor product. And the ratio will be 9:1. Again, this ratio is not a ratio that you need to know. You just need to know that this is the product that's going to be the major product. And that's our basic introduction for organic reactions.